All right, everybody, welcome to the version J for your response questions for the AP Physics C Mechanics exam. Here we're going to go through all 4 of the questions. My estimated time, hopefully probably around 20-25 minutes or so. But without further ado, let's go ahead and get started. Actually, no, sorry, first things first. If you had a different version of your response questions, they were not publicly released, unfortunately. I don't think College Board is going to publicly release them, so anything that they do publicly release, I'll go through them. But right now, this is the only version we have. So, all right. So first, you've got 2 blocks. It looks like one that's moving on a horizontal surface. The other one is inside of the hollow box. They're both the same mass. Different coefficients of friction, as well as a resistive force on the box, and we're told a couple of different things about where the cube, how the system is actually moving. So yeah, as usual, the question doesn't start till page 2. Determine an expression for the magnitude of the acceleration of the cube. I'm assuming this is just going to be as in general, so like since the cube can fall down, we have to maybe account for that as well, perhaps. Yeah, so I mean, when the 2 are moving together and the cube is not sliding down the box's surface, then the magnitude of the acceleration should just be a is equal to Fn over m. So I'm going to write that that's going to be between 0 and I believe it was t critical, so something like that. But then when the box is accelerating down, then your magnitude of the acceleration, well, you're going to have both the horizontal component from the normal force, as well as the acceleration of the cube down the box's surface, because gravity is going to overwhelm friction then. So in that case, you would actually have a is equal to square root of the x component of the acceleration, which is still Fn over m, squared, plus the vertical acceleration. The vertical acceleration would be like mg minus mu k mg. Would it be? No. No, because the normal force isn't equal to mg, right? So mu k, wait, but mu k is not even allowed in our answer. Interesting. Mu k is not even allowed in our answer, so we can't use that for after t critical. I feel like you need it, though, to answer it for after t critical. So maybe they're just asking you for the acceleration between time 0 and t critical. I think that's what I'm going to go with. Because again, otherwise you would have the net force when your cube is going down the block would look like mg minus mu k Fn, which is fine if you divide that by mass for the first term, but then again, we can't have mu k in our final answer. It's not a physical constant, so I don't know that they're really looking for that then. Also, it says determine and not derive, which means it's supposed to be a pretty quick thing. So I'm not going to overthink that one. Perhaps I'm wrong about that one, but anyway, okay, let's move on for the sake of time too. Maybe we'll revisit that if I have some sort of random thing that comes to mind. So, okay, derive an expression for Fn from 0 until immediately before the cube reaches the bottom of the box, expressed in terms of all of this. So we're, of course, going to have to start with F is equal to ma. So sum of force is equal to the mass times the acceleration, just total mass times acceleration. We can say that because these 2 things are moving together, you have negative BV must equal 2ma, because they're both going to have the same horizontal acceleration. So that kind of makes sense then. That implies that ax is going to equal negative b over 2m times the velocity of the box then. So that works pretty well. And then we can say that for just the cube itself, you also have sum of all forces on the cube equals m cubed times its x acceleration. So that's going to tell you then that normal force, negative normal force technically, should equal max, and that should equal negative b over 2 times the velocity. So that's kind of nice. And so in terms of that, though, we cannot have just v in our final expression. We actually do have to find v as a function of time. So if we go back up here, we can actually do that because this is a differential equation. So we've got dv dt equals negative v over 2m times the velocity. And the solution for that, of course, you can solve it via separation of variables. So I guess I should go ahead and show my work for that, even though I actually already know what the solution is going to look like. You have to integrate both sides, so you get ln of v equals negative v over 2m t plus c, with the condition that v of 0 is equal to v0. That means v is equal to c e to the negative v over 2mt. By the initial condition, v must equal v0 e to the negative v over mt. So putting both of these together, you end up with fn equals, let's see, v0 over 2 e to the negative v over 2mt. And this one I'm pretty confident of. So there we go. So that's kind of nice. And then for 8 part 3, we have to sketch the magnitude of the friction force. Well, we know that after T critical, it's kinetic friction, so that should go like coefficient times Fn then. But before T critical, the static friction must equal the gravitational force, and then at T critical, it should equal mu s times Fn then, because the box is just about to slip. So we should be expecting something along the lines of this. And then you're going to have a downward jump and then an exponential decay. So this should be a discontinuity here due to the coefficients of friction being different. Discontinuity, there we go. Due to the two coefficients being different then. All right, derive an expression for T critical. In terms of all of this stuff, T critical is going to happen when Fs is at its maximum value, but then it should also still be equal to mg because your box is just about to slip. So that means you have mu s times what we found for our normal force, vv0 over 2 e negative v over 2mt must equal mg. So that means that e to the negative v over 2mt equals mg 2mg over mu vv0. So that means that T critical equals negative 2m over v natural log 2mg over mu vv0. Yeah, that seems good. So pretty easy there. This is definitely more involved than the physics 1 FRQs. But yeah, here you have to say static friction at T critical is a maximum value, still equal to mg. Use your equation from Fn. So if you got the wrong equation for Fn, or if you didn't get an equation for Fn, still write this step down, right? And then just plug in whatever you got for F of n and solve for T, and they would still give you points for it. So not too bad. Let's move on then. All right. So we do have this scenario right here then, where you have 2 blocks, or rather 1 block, total mass 4m. It goes up to the top, and then it's going to split, and it looks like Q goes back to the original position, and R does not. All right. So we have to sketch the momenta of, let's see, pieces Q and R at time t1, which t1 is at the collision. Okay, so py should be 0 because it's at the top for both of them. So that's not bad. And then since block Q goes back to the original position, it must have the equal opposite as the total mass's initial velocity. So since this has 4 bars, this should be a -1 here bar, indicating same velocity as your composite system, just in the opposite direction, same speed, opposite direction. And then by conservation of momentum, this should go up to 5 then. So -1 and 5. All right, yeah, not bad. Okay, derive an expression for x2, which is that part right there. Okay, definitely a collision, so it's going to be conservation of momentum. Sum of pix must equal sum of piy. So that tells us that 4m v0 cos theta is equal to m vq plus 3m vr. We already know that VQ is negative V0 cos theta. So we get 4 v0 cos theta equals negative v0 cos theta plus 3 vr. And remember that this is all the x components of velocity. Sorry, I wrote a y there. This should be x. Good. So we can solve for that. Vr is going to equal 5/3 v0 cos theta after the collision. So that's the horizontal velocity of block r. Now we have to figure out how much time it takes to get from 0 to t2. That's not too bad because everything has a zero vertical displacement. So we can say delta y is equal to 0, and that's equal to half a t2 squared plus a y rather plus v0y times t2. So 0 is equal to negative a 1/2 g t2 squared plus v0 sine theta t2. T2 must equal 2v0 sine theta over g then. That should be a g. Sorry, I ran out of room on my paper. Put both of those together because since there's no horizontal acceleration after the collision, then that, oh wait, hold on, shoot. No horizontal, this is not the velocity after the entire time actually. So, no, I messed this part up actually a little bit. We have to find T1 and T2, no, hold on, T1 and T2 are the same. So we have to say that the velocity, the horizontal velocity of Q and R together times T1, which is half of T2, times T2 over 2, because that should be T1, plus velocity of R times T2 over 2. Got it. No, so this still works, sorry. T1 is still half of T2 because that's all vertical motion, which that's not really going to be affected by the collision. And so this is correct then. It takes half the time to go up together, so there's a velocity, and then half the time it's going down separately, so it has its other velocity. So delta x, I wish they left more room on here. I know that you have the FRQ packets on the real exam, but anyway. So that is equal to, let's see, T2 over 2 is V0 sine theta over G. So you're going to get initially V0 squared sine theta cos theta over G. I think I did that math correctly for the first term. And then for the second term, you would add 5/3 V0 cos theta with V0 sine theta. So plus 5 V0 squared sine theta cos theta over 3G then. So that's 5/3 plus 3/3, so that's going to give you 8/3. So 8 over 3G, V0 squared sine theta cos theta then. So, all right, there we go. Yeah. All right, moving on to the next page then. We've got part C. Part C says that you're drawing vertical components of the velocities. All right, center of mass should be the same. This is similar to the physics one, FRQ almost. And then pieces Q and R, we said that Q is going to reverse direction, so it goes down here. And then therefore R must go to 5/3, so probably right about there. Note too that R has a smaller change in velocity because they both have the same equal opposite changes in magnitude of momentum, or sorry, equal opposite changes in momentum. So if Q decreases more, R should increase less than. So there we go. Consider a case in which the projectile is launched, same thing, but Q falls straight down. That means that x2 must be less than x2 because by conservation of linear momentum, the horizontal, it says beyond algebraic solutions, and represent a feature of what you drew. So by conservation of linear momentum, the velocity x component of Q changes less. It would decrease less from Cm. So Vrx must increase less to ensure conservation of total momentum. So that means then that you're going to have both of the lines closer to the center of mass. Therefore, since VR is closer to VXCM and time taken to reach the ground is the same, that means that x nu must be less than x2 then. Yeah, there we go. All right, this is actually taking me significantly longer than the Physics 1 FRQs. All right, you want to term spring constant. This is not the right page. I'm missing a page here, aren't I? Yes, no. I was going to say that's part C and D of the experimental design. So, okay, so here's the experimental design. Spring, mu k, you want to determine the coefficient, and we know the spring constant, we know the mass. This is definitely going to be an energy problem then. Energy says that half k times the spring compression squared, so we'll call that delta x squared, equals mu k mg d, where d is this distance here. Yeah, so easy. We only have a meter stick then, so we're going to measure spring compression distance. We'll call that delta x, and distance traveled along rough surface. We'll call that d. Reduce experimental uncertainty, that's easy. Repeat multiple trials. We'll say, I don't know, 6 or 7 for different initial spring compression. All right, what can you put on your graphs? We would want to plot d versus delta x squared to get a linear graph, because by our equation, right, 1/2 k delta x squared equals mu k mgd. That means that I will be right back. All right. So going back over here, we've got spring potential is equal to thermal energy, so that's going to equal k over 2 mu k md, which is going to equal the slope. So then mu k is going to equal 2 mg times the slope of our graph divided by spring constant. That seem right? Move that over. K over 2, yes, that seems right. Okay. I have to always double check myself with the algebra. All right, you want to determine a new spring constant. You know a mass again. Yeah, this one's not too bad either. You're compressing the spring and measuring height, so that's going to be 1/2 ks squared is equal to mgh. So you want to plot h versus s squared, which will give you a slope that is equal to k over 2mg then. Okay. So label the axes and plot everything. So we're going to have, what did we say we're going to do? H and s squared. So h in meters, s squared in meters squared, 0, 0. And height's going to go to 0.33. So we got 1, 2, 3, 4, 5, 6. I'm going to go by 0.06. Do something like this. Okay. And then s squared is going to go to 0.01. So 1, 2, 3, 4, 5, 6. We're going to go like this. Okay. So that's our scaling, and in terms of the numbers that we have, you have to square all of your s values, which I've actually already done on the side. So we've got 0.00, oh shoot, these are terrible numbers, 0.0004, which goes up to a height of 0.02, shoot, something like that. I hate this part because I always try to do this, like there's not good scaling here. 0.0016 is approximately right here-ish, and that's going to go up to 0.13. No, I lied, that goes to 0.04. 0.0036 goes to 0.13. 0.0064 goes to 0.18, and then 0.01 goes to 0.33. All right, so right there. Yeah, that is going to be kind of a little bit of a pain to linearize, but I guess we'll try to figure out some sort of way of doing that. Let me just use this. All right, this is going to be a little bit shady, but we'll try it. Okay, yeah, good enough. That was actually not too bad. All right, draw best fit line, done. Now we have to calculate our slope. So that is going to be, let's use this point here, and I wish there was a better one to use. That's not good. I guess this one here, that's not very nice. All right, slope is equal to something minus 0.002 minus 0.06. And then on the top, we need this data point, which is 0.3 here. So that's going to be 0.24 and 1, 2, 3, 4, 5. So that would be by 0.0004. Oh man, 0.0096. I think that's correct. Okay. Let me go ahead and pull up Wolfram Alpha to help me compute that. You could use Desmos. I don't really like using Desmos too much for calculations. So that gives me a slope value of around 31.6, something like that. And we said that our slope then should be k over 2mg. M is 2, g is 10, so that gives you k over 40 is equal to 31.6. So k is going to equal 31.6 times 40, which is 1,264 Newton meters. I don't know if that's, I don't think that, no, these are small separation distances. That makes sense, I guess. Let me know what you guys got for this, actually, because I'm curious. I want to know if I'm even remotely close with that. I feel like it should be in the hundreds, not the thousands, but it's not going to be any lower than hundreds for sure. So okay, all right, and now the unicycle problem. You have an inertia, the same forces about the crank arms and two different things. Direction of the force is always perpendicular. Angular speed, isn't this trivial? Because if L2, are we, let's see. Rotational, crank arm, different lengths. Does it say anything? Yes, the mass is negligible of the crank arm. So that would mean that if you exert a force at the end of each crank arm, then omega 2 should be greater than omega 1. My justification for that is that the force is applied farther from the pivot. So you have a bigger torque, same distance and angle, for the same inertia. So the change in the angular velocity for 2 is greater than that, since omega 0 is equal to 0 for both, omega 2 must be greater than omega 1. So yeah, same torque and bigger torque, and it's also going to be, I should say, I also need to write, and both wheels have the same angular displacement. It's not same time, it's same angular displacement, because it's one rotation, not like just a set time for both of them. So higher KE change, kinetic energy change for 2, so higher final velocity. Okay. Derive an expression immediately after. Okay, so this is where we have our work energy theorem. So you're going to have work done is equal to tau delta theta. Delta theta is 1 rotation, so that's going to be 2 pi. So then that's going to be 2 pi r cross f, which is equal to 2 pi times the length, which is L1, times f, and then all of that should equal change in kinetic energy then. So work is equal to change in kinetic energy, rotational, so you get 2 pi L1f is equal to a half inertia times omega 1 squared minus 0 squared. So that means that omega 1 squared is going to equal 4 pi L1f over pi w, not omega. So omega 1 is square root of all of that, I guess. Okay. Scenario 3, oh no, it's a rolling problem. Scenario 3, a unicycle is placed on the ground such that it can move forward without the wheel slipping. The direction remains that, and the resulting angular speed after the crank arm. Okay, so now you are, oh shoot, okay. Justify, but must include, okay, so you have rolling without slipping. You're trying to figure out how this compares to theta 1. You are exerting the same torque. You're exerting the same torque, but now you also have static friction to consider. It's like if I exert a force this way, then that means that relative to the pivot, we would need static friction to go. I hate these rolling problems. I don't think I would get this one actually if I had to do this on an AP exam. But let's see. So you're going to have the unicycle crank arm. You exert a clockwise torque. It's going to rotate clockwise, which means that you have to have a force that's to the right. I think friction force would have to be to the right. No, I know this one. Yeah. I'm pretty sure I know this one. I think omega 3 has to be less because you're exerting the same torque, but now you have friction. That's the thing. Because if it's without slipping, you gotta have static friction to help propel it forward. So then, no, your pivot's no longer here. Pivot is going to be here instead. So that's going to be a bigger distance, but you need this angle. Sorry, I'm trying to work through this geometrically. You got a phi angle. Wait, no, it's the same. It's the same. I'm pretty sure it's the same, actually, by doing some geometry stuff. Because torque is equal to R cross F, which is RF sine phi, right? And based on my picture, R is going to be this thing now. It's the hypotenuse times sine of phi is going to be this horizontal, which is the same over here. So you have the same R sine phi and same force, which implies, I'm not actually sure about this one. This is just my thoughts about it. So that would imply same torque, and therefore same change in rotational kinetic energy. Now, conceptual reasoning, I would say that the torque is applied farther away from the pivot, which is now the point of contact with the ground. These are definitely harder than last year's FRQs too, but it is no longer perpendicular to the radial arm, to the vector line connecting the pivot to the force of to the point of application. So torque is still equal, and therefore delta K must also be equal for both. Okay, I think that's correct. This is the one that I'm probably least sure about in the entire FRQ. A part 1 for question 1 was also a little bit kind of tricky, I think, just because I think I was overthinking it. But yeah, let me know your thoughts of these FRQs down below in the comments. I'll do the E&M ones tomorrow when they're released. Hopefully I'll be able to get to them pretty soon after they're released, but if not, just keep an eye out for the video, please. Yeah, thanks so much for watching, guys. Have a good day.